You have advocated in recent papers, and including in your PhD dissertation, that DORIS could contribute to estimation of Geocenter. Before we delve into details, and for the benefit of the viewers of DORIS Day, could you explain what is Geocenter and why is it important?
Before that, I need to introduce a few points. We have the center of figure, the geometrical center of the Earth's surface, written CF, but in practice we only have access to the center of network CN because of the limited coverage on station crust fixed on the Earth's surface. And we have the center of mass of the whole Earth system, about which satellites naturally orbit. We have major water and atmosphere mass transports occurring over large regions, and they give rise to temporal variation of the center of mass of the Earth CM, which is observed by satellite dynamical motion, with respect to the center of figure CF, which is measurable from motion of station tied to the crust. And this motion is strongest at the annual frequency, where it mostly reflects non-tidal free mass redistribution on the Earth's surface. This orbit of the Earth is called the geocenter motion. Its expected annual amplitude is smaller than the size of a cherry, let's say 2 to 3 mm in the equatorial plane, and up to 5 mm in the direction of the polar axis. Yet, it is not necessary to take into account this perturbing effect on the modeling of ground station observation, which are tied to the crust. And these stations are used to observe the natural orbital motion of the satellites. Why do such small changes matter? Nowadays, we have new climate driving precise monitoring of geocenter motion needs, because the uncertainty in the trajectory of the geocenter motion is now the highest uncertainty in understanding the variation of the regional mean sea level and the global Earth energy water cycle. Indeed, if you want to answer the question, how much will sea level rise at regional scales over the next decade and beyond, you should be able to observe regional sea level patterns driven by anthropogenic forcing which are within 0.5 mm per year. Thus, highly stable orbits of better than 0.1 mm per year decade at regional scale are required. Given the fact that the geocenter motion is expected to vary by as much as 50 mm over the course of the century, not accounting properly for this motion will affect both satellite ultimately precise orbit determination and satellite-derived estimates of the change in the regional mean sea level. You also need a good monitoring of the geocenter motion to assess the current status of climate change and its future evolution. Indeed, it has a strong effect on measuring the change in the ice sheets, and to understand their impact on sea level and global free mass redistribution of the Earth's energy imbalance, we must explore strategies to better observe and model this subtle variation in the Earth geocenter.
Currently, there is two methods to estimate a small signal like geocenter, including satellite laser ranging through a kinematic technique or through direct estimation, or with GNSS through a combination and inversion technique. How do you estimate the geocenter with DORIS?
DORIS observation of the geocenter motion is challenging because of the complex modeling of the non-gravitational forces of the DORIS satellites. Nevertheless, the DORIS tracking network is very stable and uniquely well distributed geographically. This can be a strong asset to reduce network effects in DORIS-based geocenter time series. We yet have to consider the main source of beacon height inaccuracy. Indeed, the zenith-tropospheric delays is correlated with station heights. It's usually well known for microwave techniques. Vertical site displacement should be estimated with the inclusion of low elevation DORIS data. It is a sensible way to take into account the various error sources, reducing the quality of station heights estimates to better sense the motion of the center of figure with respect to the center of mass of the Earth. Draconitic effects should also be looked at. Errors in the modeling of solar radiation pressure can alias directly into the annual sinusoidal Z or north-south component of the geocenter coordinate. The solar radiation pressure modeling error on the JSON-type satellites can be identified and mitigated without compromising the Z geocenter estimate. Also, state-of-the-art gravity and troposphere models have to be used. And here I show you the annual estimation of the geocenter motion that we derived, projected on the Earth's surface, and you have here also its amplitude.
Over what time period have you estimated the geocenter, and how does it compare with other solutions?
With the contribution of JSON2 and JSON3, we are now able to derive a geocenter motion time series since mid-2008 with this approach. Unfortunately, the strong sensitivity of the DORIS receiver on both JSON1 to radiations in the South Atlantic anomaly area, as well as the lack of attitude measurements for the Topex Poseidon satellite, It makes it currently difficult to start another time series with these two preliminary missions. Complementary solutions were obtained using either SLR-only or GPS-only data in two previous papers with JSON2 and JSON3. They both compare very well with the DORIS-based solution, especially for the main annual signal. Yet, bias, drift, and interannual signatures remain difficult to compare between these independent estimates.
A key point raised in your papers was the use of non-synchronous satellites. You used the JSON satellites for your results so far. Have you tried other satellites, either from actual data or simulation?
Indeed, non-synchronous satellites should be disregarded. Instead, data from JSON-like satellites should be used, since any potential errors in solarization pressure modeling will have a distinct period of 118 days, which is the draconic period of JSON-like satellite. And this one is independent of the annual component of the Geocenter signal one wants to estimate, the annual component. This is shown here on the parallelogram of the Z or north-south component of the Geocenter motion we've estimated here with this approach. The most recent Sentinel-6 Michael Freilich and HY2C and D missions, or the incoming launch of the SWOT satellite, should also permit to derive the same type of Geocenter solutions, provided, of course, that the solar radiation pressure perturbations can be properly modeled. The HY2C&D and Sentinel-6A satellites are less than 1 year old, so it's still too early to look at their respective Geocenter time series.
You have proposed a working group on Geocenter within the IDS. What are the short-term goals of this working group?
Space geodetic observation of the Geocenter motion is still in its infancy. Estimating geocenter coordinates is one of the most demanding applications of high-precision geodetic techniques due to the current precision of the geodetic data and the nature of magnitude of different type of systematic error. So we will first try to derive consistent DORIS-only time series in terms of bias, annual signatures, and drift to be able to successfully combine them together using JSON2 and 3, Sentinel-6, HY2C and D, and the SWOT satellite. Independent solutions derived using different techniques have systematic differences as large as the signal level. This is why future improvements of the precision and accuracy of the ITF origin, which is the Earth's Geocenter, will depend on the inclusion of additional geodetic techniques such as DORIS and GNSS to SLR and satellites like the JSON Space-Ties platform, which has on board all these techniques. This could be very useful to validate independent Geocenter solutions.